All right, guys, welcome to today's lesson on what are called Lewis structures. And Lewis structures are essentially chemical structures that we can make that represent compounds, more specifically molecules which exist due to bonds between non-metals. So if you guys would at this point pause the video and then write down all of these steps. So there's 4 steps to drawing Lewis structures. First, we determine the number of valence electrons. Second, we arrange the atoms and we put the element that forms the most bonds in the middle. Thirdly, we begin to arrange the electrons. We make bonds, which we call shared pairs, and then we place the rest as what are called lone pairs. Those are pairs of electrons that aren't involved in bonding between atoms. And then lastly, we check to see if what's called the octet rule is satisfied. It says if not, it says change lone pairs and make them shared pairs. So I'm going to leave this up. And then we are going to be looking at how to do Lewis structures. Okay, so for example, let's start with chlorine. We'll start with an easy one. Chlorine is a diatomic molecule. So the question is, what would the Lewis structure look like? So number 1 says, first determine the number of valence electrons. Well, if you have valence electrons, you know what? Rather than switching back and forth, let me get a periodic table. Otherwise it would take a while if I switched over digitally. So on the periodic table, I look at chlorine. So you look at chlorine, hopefully you guys can see it here, and what I do is I just count across that period, and that shows me how many valence electrons there is. There's 1, 2, 3, 4, 5, 6, 7. In fact, all the halogens have 7 valence electrons. Well, if each chlorine has 7, and there's 2 chlorine atoms, that's a total of 14. So what I would do is I would write down 14. So I'm keeping track of all of my valence electrons. Next thing it says, arrange the atoms. It says elements that you expect to form the most bonds goes in the middle. Well, you guys, this is pretty straightforward. There's only 2 atoms, so how would you put them? Wouldn't you guys just put them side by side? Okay. Now it says, arrange electrons. I have to figure out where are those 14 valence electrons. Remember, we're just showing the valence electrons. Notice the first one says make bonds. So you guys, obviously, if these 2 atoms together make up a molecule, there has to be a bond holding them together, and I represent a bond with a dashed line. That dashed line represents 2 electrons. It's a pair of electrons, a pair means 2, that are being shared between those 2 nuclei, and that's really what's holding those atoms together. So if I counted for 2 electrons here, there's a total of 14, so there's still 12 more valence electrons I have to find a home for. I say place the rest as lone pairs. So you put those kind of wherever. I put 2, 4, 6, 8, 10, 12. You guys see? So and then I check to make sure I've got all 14 valence electrons, and I have. Last thing you want to do is to check to see if the octet rule is satisfied. By octet rule, you guys should realize octet should bring the number 8 to mind. And the reason for that is because the vast majority of these nonmetals, their electrons occupy a shell that holds a maximum, their valence shell holds a maximum of 8 electrons. If you guys look, if you count over, you count from here over, there's 8. Here over is 8. Somebody here would say, well, that looks like 18. But there's just a little note here. Remember, these are the d orbitals, and so if the d orbitals are full, there's d10. We don't count that. Remember, and I can't remember if I told you guys that, but the d orbitals actually are 1 energy level lower than the corresponding period. So even though this is 4s2, these are 3d10, and then it's 4p6. Since this 3d is in the 3rd energy level, we do not count those as valence electrons. So the point is 8 electrons to fill the outer shell. If you remember that, you'll be all right. So what I do is I look. So I look at this. I look at each atom to see if each atom is satisfied. 2, 4, 6, 8. That one's satisfied. Then I look at the other atom. 2, 4, 6, 8, and that has met the octet rule. This would be the correct Lewis structure for chlorine. Let me show you. So basically, we would expect a chlorine molecule, in the air, it's a gas, would just be 2 chlorine atoms bound by 1 shared pair of electrons. Hey guys, let's do another one. Oxygen is another diatomic molecule. So let's do oxygen. It's O2. Diatomic means there's 2 atoms that make it up. So you guys, we're going to use our same set of rules. Determine number of valence electrons. So we look at oxygen. I look at oxygen is right here. So hopefully you guys have your own periodic table. 1, 2, 3, 4, 5, 6. It's got 6 valence electrons. Okay? But there's 2 of them, so that's a total of 12 electrons. So I put 12. Once again, there's only 2 atoms, so I'm going to put them next to each other. What does the next thing tell me to do? Well, I make a bond. So obviously there's got to be a bond that holds them together. So that's 2 electrons. There's a total of 12. 2 already account for, there's 10 more. So then I write those as lone pairs, put them wherever. 2, 4, 6, 8, 10. Okay? So now the last step tells me to see if the octet rule is satisfied. So let's say I look at this atom, right? Because remember these electrons, and we look at them for both because this pair of electrons are orbiting both, right? So it's as if it belongs to this oxygen and they also belong to that oxygen. So I look 2, 4, 6, 8. The octet rule is satisfied for the oxygen. Let's look at the other one. 2, 4, 6. We see it is not satisfied. This is not the correct Lewis structure for O2. So what we say here is, I give you a hint. If the octet rule is not satisfied, change lone pairs and make them shared pairs. Notice we can't change the number of electrons. So what you might have to do, that's why I recommend if you guys do Lewis structures, don't do it in pen, do it in pencil because you're going to have to erase at times, okay? So what I'm going to do is take a lone pair, and you guys could probably look at which lone pair would you take. You're probably thinking, oh, maybe this. I take this lone pair, and what do? I make it a shared pair. You guys see that? So not only can electrons share 1 pair of electrons, that would be called a single bond, they can also share 2 pairs of electrons. And that's what we call a double bond. So there's 2 bonds here, a double bond. Now let's see if it's satisfied, guys. 2, 4, 6, 8. That's satisfied. Look at the next one. 2, 4, 6, 8. That's the octet rule. And so you guys see, look, you guys see what Lewis structures tell you? This is called the chemical formula of our molecule. It tells me I have 2 chlorine atoms, right? This tells me I have 2 oxygen atoms. But what does it not tell you? You guys can see, just by looking at the chemical structure or the formula, you can't tell what type of bond exists. Notice by looking at O2, there's no way I would have known that it was a double bond. The only way I know there's a double bond between those 2 oxygen atoms is by drawing the Lewis structure. And you guys can imagine a double bond is stronger than a single bond. And so it's not surprising that when oxygen forms, it's these atoms are pretty strongly held together due to them sharing 2 pairs of electrons. Let's do another one. Okay, hopefully you guys got that down. Let's do ammonia. You guys, ammonia is what you might have as a cleaner at home. We're going to do ammonia. Okay, so here's ammonia. So once again, we got to do the total number of valence electrons. You guys will find nitrogen here. And you count over 1, 2, 3, 4, 5. It's got 5 valence electrons, right? It has a total of 7 electrons, but 5 of them are valence. So all you do is go to the period it's in and count over, and that shows you how many valence electrons they have. So nitrogen has 5 valence electrons, and you guys should know hydrogen it has 1. But there's 3 hydrogens for a total of 3, plus the 5 from nitrogen is a total of 8. So now number 2. Now this is where number 2 really comes into play because now we're dealing with more than 2 atoms. It says arrange the atoms. Put the element that you expect to form the most bonds in the middle. Guys, here's how it works. Guys, look at hydrogen. Hydrogen has 1 valence electron, and in order to fill its first shell, how many more electrons does it need? Does it need 1 more electron so it would have 2 like helium? So you expect hydrogen to only form 1 bond. And then, but look at nitrogen. How many electrons does nitrogen need to fill its outer shell? 1, 2, 3. You would generally expect nitrogen to form 3 bonds. So according to rule number 2, which element should I put in the middle? You're going to put nitrogen in the middle. Okay? So then where am I going to put my hydrogens? Let's say you did this. Let's say you put hydrogens and then you did this. Careful here, guys. Okay? Do you guys think that that would be arranged correctly? So there's certain things you guys should kind of look ahead of time so it'll kind of save you some time. You know what? Right off the bat, I know this isn't arranged correctly. You know why? Because look at this hydrogen here. If I put this hydrogen here, at the very least, how many bonds does it need to form? Wouldn't hydrogen have to form 2 bonds? But you guys, in almost every case, hydrogen is only going to form 1 bond. And why is that? Because remember, it only needs 1 extra electron to fill its outer shell. So how would I arrange it? When I just put hydrogens around it. Okay, now I'm at step 3. It says make bonds. So obviously there's got to be bonds holding these atoms together. Remember, each of these dashes represents a shared pair of electrons. That's 2, 4, 6. There's 6. There was a total of 8. I still have 2 more electrons. I put that as lone pair. Where am I going to put it, guys? Hopefully you guys are, oh, I got to put it over the nitrogen. So the last thing I do is check the octet rule. You guys look at my nitrogen. 2, 4, 6, 8. Nitrogen's good. Now look at each hydrogen. Each hydrogen only has how many electrons? 2. So when we say octet, hydrogen is an obvious exception to that. Hydrogen only requires a total of 2 electrons to fill its first inner shell. All right. So guys, let's do another one. You guys, yeah, so that's all today is. We're just kind of just showing you these, and then you guys are going to be assigned some. Guys, let's do carbon tetrachloride. Carbon tetrachloride. So valence electrons. Carbon, you guys look. Carbon is right here. 1, 2, 3, 4. Okay, so that's got 4 valence electrons. And then look at chlorines. Chlorines are here. Look, 1, 2, 3, 4, 5, 6, 7. Remember the halogens have 7. So the chlorines have 7, but there's 4 of them. So 4 times 7 is 28, plus the 4 from chlorine is 32. And remember, if I'm going a little fast, you guys just pause it, look at your periodic table to try to verify what it is I'm saying. So now, the next thing is I got to arrange my atoms. The element that I expect to form the most bonds in the middle, well, you guys check this out. Carbon, I'll tell you guys right now, carbon, you guys expect, look at carbon needs 4 electrons in order to fill its outer shell. In fact, almost always you expect carbon to form 4 bonds. Because carbon forms pretty much more bonds than most other elements. So almost always you're going to put your carbons in the middle. And not to mention, you guys look at chlorine. Chlorine's a halogen. All the halogens only need 1 valence electron to fill their outer shell. Therefore, you would only expect chlorines to form 1 bond. So that being said, where would you always put the chlorines? On the outside, right? So I'm going to put the carbon here. I'm going to put my chlorines on the outside. Next step says make bonds. How many electrons have I accounted for? 2, 4, 6, 8. That's 8. There was a total of 32. 32 minus 8 is 24. So now I've got 24. So I'm going to just put in places. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That accounts for all my electrons. Now I check to see the octet. You guys, is carbon good? 2, 4, 6, 8. Carbon's good. Carbon's happy, factor 10 stable. What about each chlorine? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. It would look like this. And so how it would actually look, it would actually look something like this in 3-dimensional space, okay? All right. You guys, we're gonna do one last one. Look, it'll look kind of like ammonia, but check this one out. This one is called the ammonium ion. Now, you guys, I'm just kind of introducing one last thing. Stick with me. It's just an ion. You guys will see it's pretty easy, okay? So I'm going to do the same thing. Number of valence electrons. You guys remember we did this before. Nitrogen has 5, and each hydrogen has 1. So that's a total of 9. That's a total of 9. But now you check this out, though, guys. It has a charge. Remember, if you don't see a number there, you assume it's a 1. So how did this group of atoms acquire a +1 charge? You remember how it requires a positive charge? It had to have lost an electron. So if it normally had 9 and it lost 1 electron, now how many does it have? 8. See, guys, this still has 8. So you see it, the little extra step you have to take into account when it has a charge. Once again, I'm going to put the nitrogen in the middle. And you guys are going to get better and better at this because you're going to, oh, hydrogens only form 1 bond. They always go on the outside. See how you're going to be thinking a lot quicker. So I'm going to put hydrogen here, here. And then once again, what am I going to do? Make my bonds. How many electrons? 2, 4, 6, 8. That's all my electrons. I check the octet. Nitrogen's good. And then look, each hydrogen has a total of 2 electrons orbiting its nucleus, which is what you would expect for a stable hydrogen atom. So you guys, it would look like this. And the last thing you do, because of the charge, there's just one little last thing. You put in brackets and then you put a positive on the outside. What you're saying is the whole thing has lost total 1 electron. The 1 electron has not been lost by the hydrogen or the nitrogen necessarily, but the whole molecule has 1 less electron than it would otherwise have. All right, guys, that's it on Lewis structures. Hopefully you guys can put that into practice on the next assignment. Bye, guys.